Hi everyone, welcome to lesson 1.2. We're going to talk about neutralization equations today, which are pretty similar to what we did in lesson 1.1 with writing the sets of equations. We're just going to do a quick review here of naming acids. Now, some of you will have taken this maybe in grade 10. The grade 11 course doesn't really talk about it a lot, and yet we tend to use the naming of acids fairly regularly, so you might just kind of have absorbed it from hearing them before. But if not, we're going to go through it here. So naming acids. So the first ones we're going to look at are binary acids. So binary acids are things like when you've got your hydrogen bonded to something else. So this would be, things like HCl or HBr, etc., right? Now, for these, we're going to use the prefix hydro. You use the root of the anion. Anion, of course, is the negatively charged ion. Then we're going to add, as the suffix, we're going to add the ic, and then the word acid as well. So for an example here, we've got HCl. So we're going to use the prefix hydro. So hydro, then we use the root of chlorine. So chlor would be the root. Hydrochlor, then we add an ic acid to it. So HCl, hydrochloric acid. Let's do our HBr here as well. So HBr would be, again, hydro and then bromic acid. So hydrobromic acid. So these are all very similar. They all kind of follow the same pattern here. We're going to look at polyatomic acids. So for these ones, you're going to replace, so basically these would be things like HNO3, for example. The NO3, if we looked at NO3 minus by itself, this would be called nitrate, right? Now, when you have the polyatomic ion with an 8 ending, you're going to change that to ic and add acid. Now, if we had HNO2, the NO2 minus, this would be nitrite. Okay, so that would be the nitrite ion. We're going to add, replace ite with us. So that would be nitrous. So HNO3, we don't use hydro for these. So HNO3 is going to be known as nitric acid. So because you could also call it hydrogen nitrate. That would be an acceptable name for that. And that's what we would have gone through in grade 11 in terms of how to name that. So hydrogen nitrate, or we can call it nitric acid. So because this is an 8 on the NO3 minus, it changes to an ic acid. Now the next one would be hydrogen nitrite. So hydrogen nitrite, and because we have the nitrite, I'm going to change that ite to us. So this name is nitrous acid. Okay, so nitrous acid. So just familiarize yourself with those naming rules and make sure you can figure that out. I'm just trying to think, is there an assignment on that? I don't think there is, but it's kind of one of those things you will sort of just pick up as you use it. Now, naming bases is a lot simpler. Basically, the bases almost all have OH minus, so that's the hydroxide ion. So for example, this is simply called sodium hydroxide, right? So we would just name that. Normally, there's sort of no special ways of naming bases. Okay, oops, forgot an I here. Review. So we're going to review neutralization. Now, you definitely would have seen this in grade 10. In the grade 10 chemistry course, you would have talked about neutralization, maybe a fair bit even. And the general format is going to be an acid plus a base gives you salt plus water. So that is your general formula for the neutralization of an acid or a base. Now, for example, then, the one that we often use, so if we have HCl plus NaOH, those two things are going to combine. This will be a double displacement reaction to form salt plus water. Now, one thing sometimes people forget is that H and OH, if you've got this, that's going to make water, right? It's the two H's and an O. So this is literally our acid plus our base gives us our salt plus water. That's the general formula. Now we're going to talk about strong acids. So we have strong and weak acids. We're going to spend our first little bit here talking only about strong acids and bases. Now we normally in the past, like if you had a strong drink, for example, it would be very concentrated. But in terms of chemistry definitions, the word strong means something else. So it's not necessarily kind of is related to concentration, but not in the way that we're used to thinking of it. A strong acid would be defined as an acid that completely dissociates into its ions. So, for example, if you have 100 molecules of HCl, that means that when you put that in water, you will have 100 ions of H plus and 100 ions of Cl minus. So this 100% separates, 100% dissociates, 100% dissolves. Those would all mean the same thing. Now, there are only 6 strong acids. You do need to memorize these. So we've got hydrochloric acid, hydrobromic acid, hydroiodic acid, which I like saying. I feel like it's got a nice hydroiodic. It sounds good. Then we've got sulfuric acid, we've got nitric acid, and then this one is called perchloric. So that's perchloric acid. Okay, so make sure you memorize those. Now, strong bases are the same definition in that they completely dissociate into their ions. The strong bases are when elements from 1A and 2A, so this is from the periodic table, from the first 2 columns. The strong bases are when elements from 1A and 2A, this does not make sense. Hold on. The strong bases are when elements from 1A and 2A are bonded to OH minus. So when they're bonded to the hydroxide ion, those are strong bases. This does not include magnesium and calcium, though. Those are the exceptions to that. So magnesium and calcium are defined as weak bases. Plus, you can add another one in here, NH4OH, this is ammonium hydroxide, is also defined as a strong base. So it will completely dissociate when it's in water. Okay. Now this is what happens during a neutralization equation here. So the reaction between a strong acid and a strong base. So when a strong acid and a strong base react, they react completely. And so let's work through an example. Write the complete set of equations for the neutralization of H2SO4 and NaOH. So when I say the complete set of equations, you are going to be writing 3 equations. First, the molecular. Then we have the total ionic, and thirdly, we have the net ionic, okay? So we're gonna do all 3 of those reactions. I'm just gonna give myself some space here. Oops. There we go. Okay, so I'm gonna draw the molecular first, or write the molecular equation first. So I have H2SO4 plus NaOH. Now those are going to form, it's going to be a double displacement reaction. So I'm going to form Na2SO4 plus water. Now I'm going to use my states. I'm going to use my solubility chart here to figure out which ones dissolve, but I'm just going to give you, I'm going to speed it up here. So these do. So H2SO4 does dissolve, so it's going to be aqueous. NaOH, also aqueous. Sodium sulfate, also aqueous. Now, H2O, you wouldn't define it as aqueous because aqueous is literally dissolved in water, and you're not going to have water dissolved in water. So this is actually going to be an L, and so that stands for liquid, and so that would be a pure substance here. Now, I did forget to balance. I need a 2 here, and then I need a 2 here as well. So now I've got my molecular equation. Sorry, that's a little sloppy. It's hard to write on this. That's my molecular equation. My next step is going to be the total ionic. So I'm going to go to the next one to do that here. So total ionic. So here I'm just going to break them apart into their ions. So anything that's aqueous gets broken apart. So that means I'm going to break this one apart, and this one. The water does not get broken apart because it's a liquid. That's the pure substance, okay? So H2SO4 is first, so 2H plus aqueous plus SO4 2 minus aqueous plus, and then what do I have next? I have NaOH. So 2Na plus aqueous plus 2OH minus aqueous. Draw my bracket, and I am left with 2Na plus aqueous plus SO4 2 minus aqueous plus, and then lastly H2O, and I write that as a liquid. So that is my total ionic equation here. My next step then is going to be writing the net ionic equation. And so for net ionic, I'm going to look at my total ionic, and I'm going to cancel out whatever appears on both sides of the arrows, because those are my spectator ions. They're not going to contribute to the overall net ionic equation. So SO4, there we go. And so for my net ionic equation, I have 2H plus aqueous plus 2OH minus aqueous goes to, oops, I forgot a 2 there, sorry, 2H2O liquid. This is my net ionic equation, except what do I need to remember to do with that? Yeah, I have to reduce that. So whenever you would have, if you'll note here, the 3 molar coefficients can all be reduced. If I divide them all by 2, I get 1. So my overall net ionic equation, H plus OH minus goes to water liquid. So that is my net ionic equation, and I'll give you a hint or a little trick shortcut. For every neutralization equation, that is going to be your net ionic equation. And if it's not, you've done something wrong and you need to go back and check your work. Often, if people are going to make mistakes in this, it'll be in this total ionic equation. This is where you'll make a mistake, and basically you'll kind of do what I did, where I forgot to write that 2 in there. Oh yeah, I did that on purpose just to show you. Yes, I did that on purpose just to show you how easy it is to forget to balance it there. So be really careful of the details, and again, be sure to include all your states. Those also count. They're definitely part of this. Okay, so that would be how you would write your 3 sets of equation for neutralization reactions. Now, your assignment is exercise 2. I think it's pretty short. I think I only have, you have 3 questions where you need to write the complete set of equations for 3 different neutralization equations. So again, try that, and we'll go over it in class next time you're in. Okay, thanks guys.